Welcome to this Sigmetrics 2020 talk. My name is Benny van Hout from the University of Antwerp, and this work is joint work with Ilyas Horvat from the Budapest University of Technology and Economics and Ziv Scully from CMU. Now, the topic of this talk is load balancing, which means that we have jobs that arrive at random points in time into the system, and those jobs need to be distributed among a set of servers. And the load balancer is responsible for assigning the jobs to the servers such that, for instance, we minimize the response times. Now, there has been a lot of prior work on load balancing algorithms, and I'm just mentioning here two very popular load balancing algorithms. And what you will find is that most of this prior work focuses on servers that serve one job at a time in a first come, first served manner. Now in this talk instead, we are going to load balance across a set of servers that are called resource sharing servers. And these servers have two specific properties. The first one is that a server can serve multiple jobs at a time, but there is a limit on how many jobs it can serve simultaneously, which is called the multi-programming limit, or for short, the MPL. And in this talk we will also refer to the MPL as the threshold. So in my example here, I have a server with an MPL equal to 3, which means it can serve up to 3 jobs at the same time. If it serves multiple jobs at the same time, the service capacity of the server is divided equally among those jobs. And if there are more jobs than the MPL value, then those jobs have to wait in line to receive service. The second property of a resource sharing service is that the service rate depends on the number of jobs in service. So this means that if mu k is the rate of the server, then this will depend on the number of jobs in service, which is k. The idea behind the service rate curve is that in practice you need enough jobs to fully utilize the capacity of a server. But if you allow too many jobs in the server at the same time, then you will lose some of the server capacity due to thrashing, process switches, and so on. Now we are going to look at the load balancing problem where we distribute jobs among resource sharing servers in a heterogeneous setting. So we're going to assume that we have different types of servers, and each server type has its own service rate curve and has its own MPL or threshold value. Now the load balancing algorithm that we're going to study or analyze is the join below threshold load balancer, or the GBT algorithm. And this algorithm has actually been studied before in the heavy traffic regime. How does this algorithm work? Well, the idea is that the dispatcher is going to maintain a list of servers, and these will be all the servers that have a queue length below their MPL value. So in my simple example here, you can see that server 2 and server 4 have a queue length below their MPL value. So in this case, the list maintained by the dispatcher contains ID number 2 and ID number 4. Now whenever a job arrives into the system, the dispatcher is going to assign that job at random to any server who has a queue length below the threshold, if such a server exists. And otherwise it will just assign the job at random. This means of course that all the servers have to inform the dispatcher from time to time whenever their queue length either reaches the threshold value or it drops below the threshold value. So the main objective of this talk and of this paper is to analyze and optimize the GBT policy in a large scale regime, when we have many servers. When I say analyze, what I mean is that we want to have a simple and fast way to study the queue length distribution and the response time distribution of a job in a heterogeneous system with GBT load balancing. When I say optimize, I'm interested in how am I going to configure those MPL values in those different service types such that, for instance, the mean response time is going to be minimized. Now for the analysis, we're going to use a mean field model, and we're going to restrict ourselves to the case where the job sizes have an exponential size. Now this might seem quite restrictive, and it might appear like the results may not then be valid in practice, but in fact what we show at the end of the paper using simulation is that if the number of servers becomes very large, then the system performance appears to be asymptotically insensitive to the job size distribution. So the results that we obtain from our mean field model with exponential job sizes also applies to any other job size distribution if the number of servers is large enough. This is at least what the simulation results indicate. Now, with respect to the mean field model itself, it's characterized by a set of variables which we denote as xl of k, and this is simply the fraction of the servers of type L that currently have k jobs in their queue. And if you look at the drift equations of those variables, then you will see that this drift is discontinuous. And this implies that the mean field model, or the evolution of the mean field model, is no longer characterized by an ordinary differential equation, but is actually characterized by a differential inclusion. And differential inclusion is a generalization of an ODE, where we allow the existence of so-called hyperplanes in our space, where the drift on one side of the plane might be completely different from the drift on the other side of the plane. And this actually means that if you look at the trajectories of the solution of differential inclusion, then they might hit such a hyperplane and then perform a sliding motion on that hyperplane and then leave again. Okay. So what are the results that we actually managed to prove in the paper? Well, first of all, if we look at the system where we only have a finite number of servers, then obviously we have a stochastic system because of the Poisson arrivals, because of the exponential service times. And if you look at the sample paths of that stochastic system over a finite time scale, let's say from time 0 to time capital T, where capital T is fixed, then we show that those sample paths actually converge in probability to the unique solution of our differential inclusion. And so first of all, we show that the differential inclusion has a unique solution, and then we can rely on this very nice mean field framework by Nicolas Gast and Bruno Gogel, where they actually generalize Kurtz's theorem by relaxing the Lipschitz continuity condition that you typically need when you apply Kurtz's theorem. The question then is, can we also generalize those results to the stationary regime? And the answer is yes, provided that the differential inclusion has a unique fixed point. So if the differential inclusion has a unique fixed point, then we can prove, or we prove in the paper, that the sequence of stationary measures of those finite stochastic systems, as the number of servers goes to infinity, converges weakly to the direct measure of the fixed point. And that essentially means that if we want to know something about the stationary behavior of a large set of servers, then we can simply focus on the fixed point of the differential inclusion. Okay, how do we prove this result? Well, first of all, we rely on another nice framework, this time by Roth and Sandholm. And that framework basically indicates that we need to prove global attraction of the fixed point of our differential inclusion. And due to the exponential service times that we have, we can use monotonicity arguments, and we can use the theory of monotone dynamical systems to prove that global attraction. Okay? So we know now we can study the system by focusing on the fixed point, provided that we have a unique fixed point. But do we have a unique fixed point in general? The answer is no. And the reason for that is that when I introduced those resource sharing servers, I mentioned that the service rate, when there were k jobs in service, was denoted by mu k. And those mu k values can be any values. And so here I have a simple example of a homogeneous system with a multiprogramming level equal to 3. We have picked mu1 equal to 3, mu2 equal to 0.8, mu3 just slightly above 1. And it turns out that for those parameters, the differential inclusion actually has 3 fixed points, 2 of which are stable and 1 is unstable. So if we allow those service rate curves to be any curves, and we can make them as random as we like, then we do not have a fixed point in general. And in fact, you can even construct examples where you have 5 or more fixed points. Now luckily, in the paper we also established 2 results, one for the homogeneous and one for the heterogeneous setting, where we show that you can obtain very simple conditions that should always hold in practice on those service rate curves, such that a unique fixed point is guaranteed. And moreover, the proofs of those theorems indicate that it's also very easy to compute those fixed points. Yeah. So that concludes the analysis part of the paper. So let's now move on to the optimization problem. So as I mentioned before, the idea of the optimization problem is to find the best possible MPL values for each server type, such that we minimize some objective. And here we're going to focus on minimizing the mean response time, but the same approach can actually be used to also minimize other objective functions. Now initially, this optimization problem appeared to be not so easy. But this was basically because we demanded that all the servers of the same type use the same MPL value. Now once we realized that the problem became a lot easier if we relaxed the problem by no longer requiring that all the servers of the same type use the same MPL value, we ended up with a much easier problem. And so what we do in the paper is we present a very simple procedure that allows us to determine the optimal MPL values to minimize, for instance, the mean response time. And if you look at that procedure, you will see that the optimal solution always has the same structure. That is, all the servers of the same type use the same MPL value, except for one server type. That one server type is actually subdivided into two subtypes, and each subtype has its own MPL value. And those MPL values of those subtypes can actually differ by more than one. Now, of course, when we do this optimization, we are going to get the best possible MPL values for a specific arrival rate. And in practice, the arrival rate may actually fluctuate over time. So really doing the optimal setting for a specific arrival rate might be a bit dangerous in practice. So that's why in the paper we also indicate how we can set those MPL values in a more robust manner, such that if there are fluctuations in the arrival rate, we get guaranteed performance for a certain range of arrival rates, which should make the result also more appealing for practical purposes. Okay, so this concludes the optimization part. So let me just summarize the main takeaway messages of the paper and then discuss a bit about possible future work. So in the paper, what we did was we provide a fast and easy way to compute the queue length and the response time distribution of the join below threshold load balancer in a large-scale heterogeneous system. And the idea is essentially that we simply need to compute the fixed point of the differential inclusion, and from that we can compute the queue length and the response time distribution. We also developed a simple procedure to optimize those MPL values. And although our mean field model was restricted to exponential job sizes, we indicated using simulation experiments that as the number of servers becomes large, the system appears to be asymptotically insensitive to the job size distribution. Now, what are the possibilities in terms of future work? Well, first of all, we could make our load balancing policy a bit more sophisticated, in the sense that right now, whenever a job arrives, we assign it to any server whose queue length is below the threshold. Now clearly, when we have a heterogeneous setting, it might be better to give priority to assign the job to a certain type of server. So that might be one way to extend the work in this paper. And in fact, we believe that this can be done in a very similar way than what we did in the paper. There are also some other questions regarding more the theoretical side of mean field modeling. The first one is that, well, in case we have multiple fixed points, so if we have a metastable system, we might wonder how can we actually compute the limit of the stationary distributions? Because in this case, we do know that the limit of the stationary distributions will have support on the Birkhoff center of the differential inclusion, which essentially means that the limiting distribution is going to have support on those stable fixed points, but we do not know the exact distribution. So it might be nice if there is some way to find out what the actual limiting distribution would be. Another area of potential future work might be to generalize what we call the refined mean field approximation to the setting where the drift equations of the mean field model are discontinuous, as in this case. So when the fixed point is actually far away from the region where the drift is discontinuous, then we could simply apply the existing refined mean field approximation. And in fact, in that case, you get minor improvements, but it would also be very nice to have a method or approach that can be used when the fixed point is very close, or maybe even on the hyperplane where the discontinuity takes place. So that again, it would be a very good topic for future work. I think that concludes the talk, so let me just thank you for your attention and say goodbye.